In this video, I will be explaining you a theorem that you can find in the third unit of measure and integration. This is a very easy theorem. Okay. So here I will explain you. Here you can see the statement. If f is a bounded function defined on a closed bounded interval, closed interval a comma b. There is an interval, closed interval a comma b. Within this interval, you are defining a function that is f, and that function is a bounded function. Okay, if f is Riemann integral over closed interval a comma b, if this f is a Riemann integrable over this closed interval a comma b, then what you have to prove is it is Lebesgue integrable over closed integral a comma b. That is, if f is Riemann integrable, then f is also a Lebesgue integrable. That is what we have to prove. And the two integrals are equal, and these two are equal. That is what we are going to prove here. So the proof of this theorem is very easy. Okay. So first you have to write what is given. You can see my notes. Given. First you have to write what is given in the statement. In the statement they are given you a function f, right? And they are saying that f is a Riemann integrable over closed interval a comma b. Just write as it is. Okay. Now we have to prove what? That this function is a Lebesgue integrable also over the closed interval a comma b. That is what we have to prove, right? So just write it down. And then since they are given you f is Riemann integrable, so you are writing since f is Riemann integrable, then by the definition you can write this. Okay, this you are writing by the definition of Riemann integrable, that is supremum of, you are writing for the definition for Riemann integrable, right? So that is why you are putting r like this here, integral pi over closed interval a comma b such that pi is a step function. If it is a Riemann integrable, then you have to write step function. If it is a Lebesgue integrable, then you in the place of step function you will write what? Simple function. That is the only difference. Here you are going to see. Okay. Pi is a step function, and this pi will be less than or equal to f. That is equal to, this will be equal to what? Infimum of, you are writing for Riemann integrable, so write this Riemann integrable, write r, and integral psi. Okay, now it's psi over closed interval a comma b such that psi is a step function, and this psi will be greater than or equal to f. And also here you have to notice something important, that is when you write supremum, here the simple function will be less than or equal to f. When you write for infimum, that simple function will be greater than or equal to f. Okay, can you understand the difference? Why I am saying that is, without knowing this difference, if you are studying, then you will be confused. When writing examination, you will be confused with whether it is less than or greater than. Okay, so to avoid that confusions, I said all these. Okay, so after writing this, what we have to do is, every step function is a symbol function. We have a already you have a result like that. Okay, you are using that result here. With that result you are going to proceed further. Okay, that is why you are writing that result here. Since every step function is a symbol function, and step function Riemann integral and Lebesgue integral are same. Okay, because step function and every step function is a symbol function. Therefore, step function Riemann integrable and Lebesgue integral both are same. Okay. From that result, you can write, this can be written as it is, but only one change you have to make, that is, in the place of step function, here you have to write the symbol function. In the place of step, here you have to write symbol. That is the only difference you are making. Everything else will be there as it is. Okay, you have to write as it is. Now we know that Riemann integral and Lebesgue integral are same, right? So that is why you are writing, we know that this equal to this. So in the next line you are writing without this r. Okay, you are writing this without this r. Okay, because this equal to this. So that is why you will get this. So from this is the definition of Lebesgue integrable. Okay, this is the definition of Lebesgue integrable. So that is why at the first step you started with Riemann integrable and you ended up with Lebesgue integrable, so that you can say, so that you have proved what? The two integrals are equal. So you have proved what they asked us to prove. So hence the theorem.